start with the basics. In electronics, if you want to connect any component to another, you need some type of wire or conductive medium. And also, as you know, everything in this universe takes time to travel from one place to another. So if you want to send a signal from this place to this place, it's going to take some time. Ideally, we've been using wires, ideal wires, where there's no loss of power of the signal and there's also no time to be accounted for. Sadly, that's not the case in the real world. So that's where transmission line theory comes into play. Usually a good way to know you need transmission line theory is if your transmission line, that being some type of wire, is longer than 0.1 of the wavelength of your signal. Whenever that's the case, you should apply transmission line theory. So, a regular circuit that would look just like this with a generator, some impedance, a load, and that's it. With transmission lines would look more like this, where here we have the same generator, the same input impedance, some load, but now we have this part in the middle. That is the transmission line, and it has to be dealt in a certain way. This C0 you see here is a characteristic impedance of the transmission line. And this has a lot to do with the non-idealities of this transmission line of length D. This impedance is what happens when a wire is not ideal. A wire has some resistance and some reactive elements, which need to be accounted for in this model. This characteristic impedance changes depending on the type of transmission line. So a coax cable will have a different transmission line characteristic impedance as a microstrip on a PCB or an auxiliary cable, etc. So, continuing, we assume that the transmission line has no loss, meaning it has no resistive elements inside. Then we can model the voltage and the current using a function of position and time. You can see there's two parts to it. There's a forward propagating wave and a backward propagating wave for both current and voltage. This happens because whenever a signal gets to the load side of our circuit, it will be reflected back into a transmission line, and then when it gets to the generator side, it will be reflected back through a transmission line, eventually reaching equilibrium, and that depends on the reflection or transmission coefficients. So to get started, the voltage will come into the transmission line using this model, where the voltage coming into the transmission line won't see the load side, so you can consider only the input impedance and the transmission line characteristic impedance to get the voltage that's coming into the transmission line at first. And that's a simple voltage division right here that will give us V+, which is the voltage coming in, or V in. When that initial voltage gets to the load side, it will be reflected back into a transmission line, and that will be determined, the reflection will be determined by this coefficient gamma, which is the impedance of the load minus the characteristic impedance of the transmission line, and then the sum of those two. And you can always calculate your reflection coefficient gamma using this, nu minus old plus nu plus old, meaning that the voltage is going to the new impedance, which is the load impedance coming from the transmission line impedance. Therefore, nu, old, nu, old. The resulting reflection will be V minus, which is equal to the coefficient times the initial voltage, which was V plus. That will happen again at the generator side, and then again at the load, and then again at the generator, until it reaches an equilibrium. To help visualize this, we use a bounce diagram, which is a diagram that looks like this, where the left side of the diagram is the generator side of the transmission line, and the right side is the load. And you can see how a signal will propagate through time, and these are the resulting waves and bounces that come out of this. So you can see that the first is the Vn, comes in, gets to the load, it gets reflected back, then gets to the generator, reflected, then you add another coefficient, and so on. And that happens through time and space. The reflection coefficient of a short circuit is equal to -1, meaning that the voltage will get to the other side and then be reflected exactly the same but negative, so it will cancel out, creating 0 voltage across the short, and the reflection coefficient for an open circuit is equal to 1. So a wave will come, and it will get reflected, so the voltage will equal twice of what came in. To get no reflection, so a coefficient equal to 0, the impedance at the load must equal the impedance, the characteristic impedance. And also, it works on the generator side, where the input impedance of the generator must equal the characteristic impedance of the transmission line, and this will create a gamma equal to 0. So you could say that the transmission line is matched in impedance, and that will eliminate any reflections on any way. That brings us to today's important topic, the TDR, or a time domain reflectometer, which is a tool used by many electrical engineers to visually see and measure the reflections inside a transmission line. And it is a very useful tool that will literally tell you how far along the transmission line you may be having a short. That tool is basically this part in the circuit, where you connect a transmission line to it, and you can connect whatever you want on the load side to measure the reflections that you're getting. And the TDR will generate some voltage that it can then measure back, and it has some input impedance, and it's got a voltmeter that measures the reflections very accurately, very fast. So with this very useful TDR, you can see this handy table in real time. This table right here will show you how a transmission line reacts to different loads. So basically, the TDR will be measuring the voltage in, so the voltage on the generator side, which is this graph right here. As you can see in the first example, where the load is a short, you will have a voltage going in, and then a reflection will cancel out that voltage, creating 0 voltage across. When the case is where the load is an open, you will have voltage coming in, and then a reflection that will double the voltage, creating double the voltage that came in. When you get into reactive elements, like a capacitor, that we see here, it changes a little bit. So you get a voltage coming in, and then the capacitor affects the voltage in this way, which is a exponential type of curve, where it will take some time for the voltage to change into the equilibrium voltage. And for an inductor, it's the same case, but it is a opposite of the capacitor, where the voltage will decay into 0 volts with an initial spike. Also with the capacitor, it's the same case. It has an initial spike down. If you don't have matched impedances at the load, then you get different voltages, like we can see there. And in the capacitor and inductor, if you have a unmatched impedance at the load, that we see here, with the inductor and the capacitor, then we will have the same response of the capacitor and inductor, the same curves, but they will reach the equilibrium voltage, which is now lower because of the unmatched impedance that's parallel or in series with the capacitor and the inductor. In the case where the load is matched with the transmission line, then you would see a straight line, because the equilibrium voltage will be the same as the input voltage. There are differential equations associated with the reactive solutions, and that's a little bit more than we're getting into today, but there's a solution where you can track that change with time. It is important to realize that a transmission line will reach an equilibrium eventually, so if you give it enough time, the voltage and current will be the same as if there was no transmission line. So going back to the original circuit with a generator, an input impedance, and a load impedance, and that's when it reaches equilibrium. So what happens when you have a problem where you have your generator, as always, an input impedance, then a transmission line, a resistor, a capacitor, another transmission line, and a load, all connected through ground. It is given that these are all the same. The two transmission line impedances and the load impedance is the same. And then the capacitor A, the resistor A, is equal to 0.6 of the impedance C0. When the signal coming from the generator travels through the first transmission line, the circuit can basically be modeled like this. where A is the resistor, B is the capacitor, and C0 is the characteristic impedance of the second transmission line. So we get a voltage coming out of the first transmission line, which equals VJ1. That's going to go through this circuit, and then we also need the voltage VJ2. VJ1 is going to be the input to this system, and then VJ2 is going to be the output or where it comes out. So you can clearly see that the new impedance that VJ1 is going to be subjected to is equal to A plus B parallel with C0, which would equal 0.6 C0 plus the capacitor value parallel with C0. Capacitor impedance, I must add. So 1 over J omega Z. The new reflection coefficient will be, like we said, nu minus old over nu plus old. So that's our new reflection coefficient. And our transmission coefficient will be equal 1 plus the reflection. We know that VJ1 will be just equal to the voltage in from the generator times the transmission coefficient, so whatever was not reflected back to the generator. And that is equal to Vn, or V plus, which is also named, plus 1 times 1 plus tau. With this information, we can turn Vj2, which is a simple voltage divider of Vj1, across the parallel of the capacitor paralleled with C0, over that same parallel plus the resistor A, which equals 0.6 C0. Now with this, you can do the same thing for the next transmission line, which will have VJ2 as the input. And that will go to the load, and you can get the coefficients the same way as we got here with the same idea of gamma equals nu minus old over nu plus old. Gamma will always span -1 to 1, so that's a good way to know if you're getting your coefficients correct. After getting all your coefficients, you can do a bounce diagram, and then that will help you see what's going on in the transmission lines and how the overall circuit will eventually reach an equilibrium.